Okay, let's do an example of optimization problems. A farmer plans to enclose a rectangular pasture adjacent to a river. The farmer has enough material to make a fencing of length 100 meters, and no fencing is required along the river. Find the dimensions of the pasture with maximum area. Okay, so basically what we have is a river, something like this, and then we want to have a fencing, something like this. This is rectangular. This side we don't need anything, so on the river side we don't need anything, but here and here we need fencing. So here, so step one, as always, identify the variables. Here, identify the variables, the quantities of variables involved. Variables. So here I will have a width. Let me call it x is for the width of the pasture. So here basically y is for the length. What else? We have area. So area of the fencing. So let me put A. So area of the enclosure. Okay, so that's the first step. Step two is, well, find the relations or equation. Find the relations. The relations. Well, here, one of the given information is that the fencing material that farmer has is 100 meters. So that means that if this is X, the fencing length is this part, yes? So it means that the total fencing is x plus y plus another x. In other words, it is 2x plus y. And we know that we only have 100 meter of material to make that fencing. Another thing is that the area is equal to, well, x times y. Specifically, a is the variable to be maximized, the variable to be maximized. So we need that specific. Okay, so we have now two equations. Then the next step or third step would be, well, make one equation for the variable to be maximized. So make find the equation for a in terms of only one of the variables. Okay, so here means that, well, a is now a function of xy. We will use this equation to make a function of one of these. Well, let's say a function of x. Well, here, so since we have 2x plus y equals to 100, I can write y in terms of x and then take this and put it here. So a is going to be x times 100 minus 2x. This is the equation, the function to be maximized. That's the main thing. But our modeling is not done unless we find all the possible values. So find the domain for possible values of x. Well, something to notice is the x is length, so it needs to be always x is positive. Well, we can say or 0. Yes, that's the best we can get. So this means that x is always bigger than equal to 0. How about y? Oh, sorry. How about the other condition? We know that 2x plus y can be equal to 100. At the maximum possibility for x will happen when y is 0. In other words, when you make this very long rectangle like that, something like that. But the max it can get, y can be very close to 0 or 0, then in that case x can be 100 over 2, which is 50. So x is going to be less than equal to 50 meters. That means that we have the function and the domain. So values of x coming from the interval 0 to 50. Okay, so this has now everything. We need to find the maximum. So this is the next step. Find the last step. The modeling is done. Now we want to find the absolute max of x times 100 minus 2x on the interval 0 to 50. Okay, so it means what? We have a function, say a at x, and we have a closed interval. We know that always we will get absolute max mean. To find absolute max mean, we need to find first critical points. In this case, it is, well, find derivative. It is 100 minus 2x plus x times negative 2. This gives us 100 minus 4x. Set it equal to 0, then means that x means can be 25. That's a critical point, and it is in the interval. Then endpoints. These are 0 or 50. To find absolute max mean of a continuous function on a closed interval, we check the critical points and endpoints and then see which one is the max, gives us the max value. So evaluate the function at the above points. While a at 0 is 0 times 100 minus 2 times 0, this is 0. A at 50 is 50 times 100 minus 2 times 50. That's again 50 times 0, which is 0. How about the critical point? A at 25 is 25 times 100 minus 2 times 25. And that gives us 25 times 50. And as you can see, this is the max value for AX. In other words, the max value, the max area occurs when x is equal to 25, and since we have x, we can use let me zoom in a little bit, zoom out. We have relation between x and y here. This is the relation between x and y, and then we can say that from there we have y equal equals to 100 minus 2 times 25, which is 50. So the dimensions at which the critical the maximum area of closure happens is when the widths are 25, the length is 50. Well, that brings us the final result. That's what we were looking for. Yes, looking for the dimension. Remember again, there are two important points. One is, oops, not there. One is the modeling. The other one is the finding max